All right, welcome to Unit 5.12. We're going to continue using the logarithm function to solve exponential equations, and here we're going to incorporate questions where we're looking at real-world situations. All right, to get started, let's go back and take a look at some of the questions that we were working on in class. So pause the video and work through these 1, 2, and 3. They may seem tough because you just need to refresh your memory on what logarithms are. So go back, look back at your notes and use those and really persevere to get these answered on your own and only then move on. All right, so here we'll take a look at the answers and I'll kind of work through them very briefly. So the first one I want to know is natural log of 135.7, is that equal to 4.91? And realize that what this is saying is log base e of 135.7 equals 4.91. And what this means is if I raise e to the 4.91 power, will that be equal to 135.7? Remember, I can rewrite this logarithm equation as the base raised to the exponent equals 135.7. And I can use Wolfram Alpha or my calculator to raise e to the 4.91, and while I'll get something very close, I won't actually get 135.7. So there I would have to say no, they are not equal. All right, here more work with inverses. So if I sketch a graph of the exponential function 3 to the x, that's pretty simple. It's an exponential function that's increasing. Exponential growth there. And then we want to sketch a graph of the inverse. Now remember, the inverse is where I switch the roles of the input and the output. So what I'm doing is I'm solving for x, and in doing that I'm going to get the logarithm function. So I'm going to get x equals log base 3 of y. Well, let's go ahead and graph that. So my input here is now y values. So when I input y values, I'll have 1, 3, 9, things that make it easy to compute. And of course, log base 3 of 1, well, what must I raise 3 to the power of to get 1? 0, right? So there we go. And what log base 3 of 3 is 1. Log base 3 of 9 is 2, right? It's going to work upwards like this, and as I move to the left, I'm going to get closer and closer to negative infinity. And let's explain why that is, right? I can never plug in a value of 0. Log base 3 of 0 doesn't exist, right? There's nothing I can raise 3 to the power of to get 0. Look back at my original function. 3 to the x will never, ever actually touch 0. But as I get closer and closer to 0, for example, what is log base 3 of 1 over 27? Well, what must I raise 3 to get 1 over 27? And the answer is negative 3. Right? Because 3 to the negative 3 is 1 over 3 to the third, which would be negative 27. So it'll go downward like that. All right, this last one has a lot of working parts to it. So I have this exponential function defined here, and it gives me some points. So it says, okay, when you plug in these x values, this is the output that you get. And we want to find the value of log base 13 of 371,293. So in looking at this, I realized that I want to be looking for the value of a log base 13. And notice that in my function here, I have 13 as the base raised to the x. And so I know that when I find the inverse of this, when I solve for x, I'm going to have a logarithm function with a base 13. So let's go ahead and solve for x so that we get a log base 13 function. Because if we do that, then we know some points that are log base 13. So when I solve, I'll just keep it as f of x because that's how it is in my table. I'm going to end up, here are my steps here, as x equals log base 13 of 2 times f of x. So think about what this is saying, right? This is saying if you plug in an x value, it'll be equivalent to log base 13 of 2 times f of x. And we want to know the value of log base 13 of this number. So we want to somehow find a way to make 2 times f of x equal to 371,293. Well, the argument of my logarithm function is 2 times f of x. So are there any f of x values which when I multiply by 2 will equal 371,000? And I can try and I can go through and I can find that when I multiply 185,646.5 by 2, that's going to give me 371,293. And we know the corresponding x value, right? So the corresponding x value will be 5. So I can say that log base 13 of 71,293 will be equal to 5. And it's important to also remember what that means, right? That means that if I take 13 and I raise it to the 5th power, it will be equal to 371,293. All right, now we're going to go ahead and apply some of the work that we've been so diligently working on and the methods that we've learned to some problems which include real-world context. All right, here we go. So a population of bacteria is growing according to the equation P of t given there, with t measured in years. How long will it take for the population to exceed 8,000? So pause the video here, try doing this all the way through yourself. You can definitely do it, so give it at least a couple of tries, and then we'll talk briefly about it. All right, so just to make sure we understand what we're looking for, we're wondering how long it will take, meaning we're trying to solve for t. We want to know when the population will exceed 8,000. So if you're feeling up to it, an easier way to do this is to, instead of setting it equal to 8,000, to set your population greater than 8,000. But we can do this by setting it equal to and just remembering that we actually want to know when it's greater than 8,000. So we'll come back to this at the end. So we have our population, P of t, and what we want to do is see when it will be 8,000. And it's key to also make sure that we know it's growing, right? We know that because the b value is greater than 1. So we have 1,600 e to the 0.21 t equals 8,000. And we can go through and solve. I forgot the t there. Okay, so go through and solve. What I'll do is I'll divide by 1,600 on both sides. So I'll have e to the 0.21 t equals 8,000 over 1,600. And at this point, we can solve for my exponent by using the log, right? We know that the exponent will be log base e of 8,000 over 1,600. So I have 0.21t, my exponent, is equal to log base e of 8,000 over 1,600. We're almost there. Now what we've got to do is divide by 0.21 on both sides. And so I'll end up with t being equal to log base e of 8,000 over 1,600 divided by 0.21. And so you can go on to Wolfram Alpha and actually have it compute this. So let me explain briefly how to do that. All right, so in Wolfram Alpha, you can enter this by using the command, just using log, and then in parentheses, you're going to put in 2 arguments. So you're going to put in the base followed by the argument, right? So my base would be e, and the argument is 8,000 over 1,600. And in Wolfram Alpha, I can also say that I want to divide by 0.21, so I can then put divided by 0.21. And what I'll get is that this is equivalent to about, approximately, so I'd include approximately here, 7.66. So coming back to my answer here, t is the number of years it will take for my population to equal 8,000. I want to know when it will exceed 8,000, and I know it's growing. So once the population of bacteria has been around for longer than 7.66 years, it will exceed 8,000. So make sure you have your answer written down. All right, now we have a couple more. I'm not going to go as in-depth, but we'll talk briefly about each one. Okay, so here we have a similar problem, except the population is decreasing. And the question asks, when will the population be at 300,000? So just like in the last situation, we want to have an equation for the population. So we don't have that yet. So step one for you to do is going to be to write an equation for the population. So what is P of t? And then step two, you want to solve, and you want to set it equal to 300,000, right? Then you want to set it equal to 300,000 and solve there. So go ahead and do that on your own. We'll compare answers tomorrow, and we have a couple more to look at. All right, here we have bismuth-210 is an isotope that decays at 13% each day. We want to know, what is the half-life of bismuth-210? So I'm not going to say too much here, just that once again you can set up an equation knowing that it's decaying by 13% each day, and think about what it means to find the half-life. Okay? And lastly, we have a situation where at a constant temperature, the atmospheric pressure P, which is measured in pascals, is given by the formula below, where H is the altitude in meters. Rewrite the equation for H in terms of P. So here we have the equation. I want you to rewrite this as H in terms of P, and I want you to post your formula, H, in terms of P, in your comment along with your question or your answer. All right?